Let's talk about RSA encryption. So I wrote the steps out here. It gets a little complicated because there's some math involved, but essentially it uses prime numbers and modular arithmetic, the similar way the key exchange did, but there's a little bit of a difference to it. You start off by picking two primes, which you call P and Q. Then you multiply them to get this number N equals P times Q. Now, the basis of this encryption method is that if P and Q are very large numbers, then you have some number N, but it's very difficult to figure out what P and Q are. If you've ever done a prime factorization of a number, you basically have to go through and brute force it. Is the number divisible by 2, 3, 5, 7, 11, and so on for every single prime up to the square root of that number. So knowing N without P and Q means it's difficult to find P and Q. But if you know P and Q, then you can use math to find these special numbers E and D. I won't go into the math of that because it's pretty complex. But you can find these special numbers E and D such that for any number M, if you raise that to the E times D power and then do mod N, this one, you get the number back. And so this is our basis of encryption, is modular arithmetic. When you do the number to this power mod N, it always gets the same number back instead of a different number. Then you keep P, Q, and D all secret, so no one knows these two factors, and they don't know one of these two special numbers, whereas N and E are sent out publicly. So you send out this number, which is very difficult to factor, and you send out this number, which has no meaning outside of knowing what P and Q are. To encrypt a secret number M, you compute S equals M to the power of E mod N, and then to decrypt, you take this, raise it to the D power, and do that mod N, which, if you follow through here with the modular arithmetic rule, means it's basically the same as this, which means when you've done both of those, you get the value M back. So you can encrypt a message using this special number E, which is sent out publicly, and then you can decrypt it using your secret number D, which only you know. Let's do an example of that, and let's write this one nice and big so we can work through it. Suppose Alice picks primes 53 and 59, right? Okay, so P equals 53, Q equals 59. Then this step, we multiply them. We calculate N equals P times Q. So if you multiply 53 times 59, you get a total of 3,127. So N equals 3,127. Next step, use math to find special numbers E and D. Well, we won't go into the math of that, but ... we find that E equals 3, so that's easy, and D equals 2011. Here are all of our numbers. Here are the ones that we keep secret. P, Q, and D. So P equals 53, Q equals 59, and D equals 2011. And then publicly, we release the numbers N, which is 3,127, and we release the letter E, which is 3. So now, suppose Bob wants to send a secret message to Alice. Bob's secret message is 50. In practice, all these numbers would be much, much bigger, but then we can't do them on a standard calculator. The number 50 would be encrypted for some sort of alphanumeric thing or something that a computer could read. But basically, Bob knows N and E. So Bob calculates. N and E are public. So Bob comes over here and encrypts S equals M, the secret number 50, to the power of E, the power of 3, mod N, which was 3,127. So 50 cubed is 125,000, and we compute that mod 3,127. So divide by 3127, 39 and change, so subtract the whole number part, and then multiply back by 3127, and we get 3047. So this equals 3,047. So Bob sends 3,047 to Alice. To decrypt, we'll go over here. Alice is going to compute S, which is this number, 3,047, to the power of D. D is Alice's secret number that no one else knows, to the power of 2011, mod our special number N, which was 3,127. This 3,047 to the power of 2011 is not something we can do with a standard calculator, but a computer can do it just fine. But the point is that when you do this, this works out to 50. So Bob encrypts the number 50, this way, Alice decrypts it this way, and you get the number 50 back. You notice that after you come up with P and Q, you don't really need them anymore. Here are the important numbers D, N, and E. But you want to keep P and Q secret, because if someone knows P and Q, then they can figure out D and E, and then they can figure out how to decrypt your messages. So you have to keep these primes private. And this is useful because you can come up with these numbers on your own, and then you can send these to someone and say, send me a secret message, encrypt it using N and E, and they can encrypt it using the numbers you gave them, but only you can decrypt it with the one you kept secret. So this is great for when communication is not happening in real time, if you send someone a message and there's maybe a bit of a delay before they write back.